Welcome. In this video, we're going to talk through some periodic trends. This is part 2 of our periodic trends series, where we're going to talk about a few topics being the successive ionization energies, radius of ions, and then exceptions to some of those periodic trends that we observe. So first, let's take a look at successive ionization energies. And what that means is the energy to remove the first electron versus the second, third, fourth electrons. The first ionization energy is the energy to remove one electron from a neutral atom. You could also have something called the second ionization energy, which would be to remove a second electron once it's already lost one. So basically what we're doing is removing an electron from +1 cation. And then the third ionization energy would be the energy to remove an electron from the +2 cation, and so forth. So for example, the first ionization energy would look like this. So neutral sodium would be turning into the sodium +1 ion. The second ionization energy would be the sodium +1 ion losing a second electron. And then the third would be a sodium +2 ion losing a third electron. And this might look weird to you because you might say, what? Sodium doesn't form, a +2 or +3 ion. And we're actually going to see why that is if we look at the energies it takes to remove these various electrons. Because let's take a look over here at sodium. Here's a graph showing the first, second, third ionization energy. Notice the first ionization energy of sodium is 496 kilojoules per mole, whereas the second ionization energy is 4,500. So it's 10 times as hard to remove that second electron from sodium as the first one. And then the third one's even harder, it's 6,900. So this first electron is that valence electron. This one ends up being much easier to remove. And this is why we end up only seeing sodium actually lose one valence electron. That second electron is so much harder to remove that it typically does not happen. Looking over here at magnesium, magnesium has 2 valence electrons. And notice how its first ionization energy is 730. The second one, it's harder, but it's maybe about twice as hard, 1,400 kilojoules. But the third electron is now no longer in the valence shell. And notice how it's way harder to remove this third electron. So typically when magnesium forms an ion, we see it forms a +2 ion. And that's because these first 2 electrons are much easier to remove, being in the valence shell. This third electron is much harder to remove. So that's why sodium typically will just lose 1 electron. Magnesium will typically lose 2 electrons. So that's one thing we take away from this data set. Here's another way of presenting this data. We're looking at a bigger set here. We have all these elements, sodium, magnesium, aluminum. We're looking across the third row on the periodic table. And if you notice the successive ionization energies, the valence electrons are in blue and the core electrons are in red. And what you'll notice if you compare the valence versus the core electrons, you'll see a large jump in the ionization energy. There's a big difference in removing a valence electron versus a core electron. So like for aluminum, its first 3 electrons are relatively easy to remove. And then if you want to remove that 4th electron, it is about 5 times harder. Silicon, its first 4 are relatively easy to remove, and then it's like 4 times harder to remove that core electron. So we'll see a big difference in the ionization energy for a valence electron versus a core electrons. Core electrons have much higher ionization energies. All right. And if you think about why that is, I guess I don't really have a visual on here, but it's because they're going to be, closer to the nucleus. Like let's look at, sodium right here. Its valence electron is currently in, the third shell. It's experiencing an effective nuclear charge of +1. If you look at its second electron, so once it already loses, because remember this is sodium, is 1s2, 2s2, 2p6, 3s1. Here's its valence electron right here in the third shell. Once it loses that valence electron, if it's going to lose a second electron, it's now coming from the second shell. So now it's coming from the 2p. It is much closer to the nucleus. And we know that when something's closer to the nucleus, it's going to increase the attraction there. So these core electrons are closer to the nucleus. They're feeling a much stronger attraction to the nucleus. That results in a much higher ionization energy. Also, if you were to calculate the effective nuclear charge for these core electrons, you'll see the effective nuclear charge has actually gone up a lot because once it's already lost a electron, here's its new electron configuration. So now this electron configuration is looking kind of like neon, right? So it only has 2 core electrons. So if you were to calculate the effective charge for this second electron, it ends up being there's 11 protons, and now there's only 2 core electrons, because remember we lost a whole shell. So now my second shell is valence. So the effective charge is +9. So again, that's why the second electron is 10 times higher attraction to the nucleus. It takes 10 times as much energy to remove the second electron, because it's closer and it's experiencing a greater effective nuclear charge. So something we can tell from our successive, if we look at a series of successive ionization energies, with this knowledge that we have that core electrons are harder to remove than valence electrons, we can actually analyze a pattern of data and figure out how many valence electrons this element has based on its successive ionization energies. So what do you want to look for is you want to keep in mind that core electrons are going to be much harder to remove than valence electrons. So you're going to see a big jump in ionization energy between a valence electron and a core electron. And if you're wondering, is there a certain number we're looking for? Does it have to be 5 times as hard or 10 times as hard? There's not really, it's going to vary by atom. So you just kind of have to scroll down that set of data and see where do you see a big increase. So like if I scroll on this data set for element A, so this is an unknown, I'm trying to identify what it is. Notice how the first to second ionization energy, that gets about twice as hard. The third is about twice as hard as the second. The fourth is a little less than twice as hard. And all of a sudden going from the fourth to the fifth, this is a really much bigger change than the other ones, right? So this is maybe like 6 times harder. We don't have to calculate what it is exactly, but it's a lot harder as compared to like these changes right here. There's a pretty dramatic change. So what I'm going to assume from that one is that this electron is a core electron, whereas these electrons over here were all in the valence shell. So I can look at this and say, oh, it looks like my element A has 4 valence electrons. So if I were to look at a periodic table, I can narrow down my choices of what this element might be. So like maybe this element is carbon or silicon, or germanium. Maybe it's something over there in column 4 on my periodic table. All right, let's take a look at another one. B, going from the first to second, they're maybe about twice as hard, but comparing the second and third ionization energy, it's 4 times as hard, whereas these ones are all maybe less than doubling. So where do we see the biggest difference? It's right here between the second and the third. So that tells me that while these electrons are valence, these electrons over here must be core because they are much harder to remove. And these ionization energies, I just realized the units are not labeled on this table. These are typically given in kilojoules per mole. So it's the energy needed to remove per mole there. So I could look at this data and say, oh, element A has 4 valence electrons, element B has 2 valence electrons. So again, our takeaway is core electrons are much harder to remove than valence electrons. They'll have a much higher ionization energy. Now let's take a look at comparing radius of ions. If you're comparing a cation and its neutral version, you will see that cations will have a smaller radius than the neutral version. And one way you can think of this is that they have lost a shell typically. So like if you compare lithium versus the lithium ion, lithium is 1s2, 2s1. The lithium ion is just 1s2. And since they're both lithium, they both have, 3 protons in their nucleus. But the lithium ion has those 3 protons. It only has to attract in these 1s electrons, whereas over here in the lithium, it's got the 1s and the 2s. So we're losing a whole shell of electrons typically. So it's going to give us a smaller radius for our cations. And looking at anions typically have a larger radius. And the reason why here is because when you form an anion, you're gaining electrons. So you're adding electrons, and electrons repel each other. So when you add electrons, you're increasing that electron-electron repulsion. So the electrons are going to end up spreading out. So if you compare fluorine versus the fluorine anion, your fluorine anion has more electrons, right? So it's got more repulsion. It's got 6 electrons in that 2p subshell, but they both have the same number of protons attracting them. So they're both fluorine. They both have, 9 protons in their nucleus. So we'll see the fluoride ion, the -1, ends up being larger because its electrons are going to spread out because we've got more repulsion there in the 2p. Okay. Let's look at some examples with things that are isoelectronic. So isoelectronic is when you have the same electron configuration. And this is something we'll notice, like if you look on your periodic table, you'll notice the sulfide ion, the chloride ion, the potassium ion, the calcium ion, they all end up being isoelectronic with their nearest noble gas. So they're all isoelectronic with argon is that nearest noble gas there. But they all have, so they have the same electron configurations, right? Those are highlighted there in gray. But what's different about them is their number of protons, because different elements have different numbers of protons there. And notice that calcium has the smallest radius and it has the most protons, whereas sulfur has the largest radius and it's got the fewest protons. So when you're comparing two elements with the same, electron configuration, the one with the more protons in the middle, it's going to have more attraction, right? There's a greater attractive force. So it is going to end up with a smaller radius. Also, if you were to compare, let's say, the ionization energy of one of these outer electrons, you'd notice it would have a larger, ionization energy for that ion. But often we're comparing the radius here. So notice how calcium's got the most protons, so smallest radius, least protons, largest radius. And in this case, we can just focus on the protons and nothing else because their electron configurations are the same. They got the same core electron, same shells, everything else is the same. The only difference is how many protons are in their nucleus. So looking at some practice problems, which has a larger radius and why? Let's compare sulfur versus the sulfur ion. They both are sulfur, so they both have 16, protons in their nucleus. So let me write it this way. 16 protons, 16 protons. Okay, and the sulfur has this electron configuration. It's neon 3s2, 3p4, and the anion is neon 3s2, 3p6. So what we notice is the shells are the same, the protons are the same. The only difference is the number of electrons. That's the only thing different about it. And we know if we're adding electrons, we're increasing the repulsion because electrons repel each other because they're both negative. Electrons repel because like charges repel. So negatives repel each other. And so that's going to make our S2 minus bigger because why? They're repelling each other. So that means they're going to spread out. They're going to try and get away from each other because they don't like being together. All right, how about magnesium versus the magnesium ion? Magnesium, you can't see it on the periodic table here, but magnesium has 12 protons. So will the magnesium ion, because that doesn't change. The neutral magnesium is 1s2, 2s2, 2p6, 3s2. The magnesium ion, it will have lost those valence electrons. So the magnesium ion is going to be smaller because it has the same, number of protons, but it has fewer shells. So I would say my neutral magnesium would have a larger radius. So they got the same protons attracting, but magnesium ions, electrons, they're attracting in the second shell versus the third shell. And let's look at one more here. If you're comparing the oxygen anion versus neon, oxygen has 8 protons, neon has 10 protons. In this case, they're both isoelectronic with each other. So it's 1s2, 2s2, 2p6, and they're both the same. So if you look at the things that are the same, they've got the same shell, they've got the same, core electrons, all that good stuff is the same. What's different, though, is just the number of protons. So neon has more protons, so it's got a greater attraction, so it's going to be smaller. So who would have a larger radius? Whoops, I forgot. I'm supposed to circle who's larger. Oxygen would have the larger radius because it has less, attraction to its nucleus. That's okay. Noble gases, something you might notice about them is that they've got really high ionization energy. That's because they got the greatest effective nuclear charge here on the table. Their effective nuclear charge ends up being +8 typically, except for helium. It's a weird example. And they don't typically form bonds. They don't tend to accept extra electrons because their shells are already full. So notice they have something called positive electron affinity. If you look back to your notes on what an electron affinity is, basically means that they don't really want to accept electrons because their shell's full already. No thanks. And then last thing, I'm going to talk about some exceptions to the trends here. So if you look in this trend, like in general, going across a row, we say the ionization increases, right? But there's actually some dips along the way. It's not just like a straight increase across the row. There's a little dip right here, and there's a little dip right here. So we're going to talk about what explains these little dips right there. You don't have to memorize the dips necessarily or predict them, but you might see a scenario where you're presented with this information and you need to explain why. So why does oxygen's ionization energy a little less than nitrogen's? So let's take a look at that one first. Why does oxygen have a lower first ionization energy than nitrogen? So, because if you look at what we've been talking about so far, you'd say, hey, they both have electrons in the second shell. Oxygen has a greater effective nuclear charge, right? If you look at their effective nuclear charge, we'd say that, oxygen's is +6, whereas nitrogen's only +5. But it looks for some reason like oxygen's electrons are a little easier to remove. And if you look at why, here's where orbital diagrams can help us out sometime. So if we compare oxygen versus nitrogen, and so if I'm trying to explain something like this, I'm just looking for like, what's different about them? So if I can't spot it right away, I'm gonna write out their electron configuration and then maybe the orbital diagram to help me spot the difference. And when I write out the orbital diagram, I can spot the difference here. And what oxygen has that nitrogen does not is a pair of electrons in the same orbital here. And we know that electrons are negative, so they repel each other. So 2 electrons in the same orbital, not ideal. That causes some extra repulsion because these like charges repel. So that's what's happening here. That's why oxygen's electron is a little easier to remove than expected, is because of that extra repulsion from them being in the same orbital. Okay. And here's another visual saying the same thing. So again, having that extra, we're removing an electron that is in a shared orbital. These electrons being paired up, they are repelling each other. So this ends up being, easier to remove because that pairing, that sharing of the orbital causes some repulsion. So that's why we see this little dip here going from nitrogen to oxygen. Next, we want to talk about is this little dip here, like beryllium and boron. To look at beryllium and boron, same thing. You expect boron to have a higher ionization energy because they're all in shell 2. Boron's got an effective charge of +3, whereas beryllium's only +2. So you expect boron to have a higher ionization energy, but it doesn't. It's actually slightly lower than beryllium. And again, you're trying to figure out, well, what's different about them? Well, they all have their valence electrons in the second shell, but we also know that borons are actually in the 2p, whereas beryllium's in the 2s. And normally we ignore this difference because normally, most of the time, it's like not really that significant. But here is where we actually see a little bit of an impact here. So what I'm seeing based on this data is it looks like these 2p electrons are actually a little bit easier to remove than a 2s electron. So the reason why we actually see a slight dip going from beryllium to boron or magnesium to aluminum is because these 2p electrons are a little bit further away from the nucleus. So they are, a little bit easier to remove. But it's just right here that you notice that kind of dip. All the way down the rest of the row, it's kind of, it's not that significant. Okay, so that's what's going on here between your beryllium and your boron. And again, this is also an example from an old AP release problem, these two scenarios. So beryllium versus boron, they both have their valence electrons in the second shell. So you're trying to figure out what's different about them. Well, we can see that boron's valence electron, first electron to be removed is actually in a 2p, which is slightly easier to remove. It's slightly higher energy. That just means like basically further from the nucleus, makes it easier to remove. All right, and that's it for our notes. Thanks for watching.